तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We had discussed about positive feedback, which is regenerative, and we said this is a very useful configuration with memory, that is hysteresis. The circuit understands how the input is varying, whether it is increasing or decreasing. If the input is increasing, it changes state at a particular point, and if the input is decreasing, it changes state at another point. So, this is what is called as memory. The same circuit with this end grounded and with input connected here, let us say this is R1, R2. R2 is the resistance from the output coming to the non-inverting input, and R1 is the resistance which had gone to the ground. Instead of grounding it, we are connecting it to Vi, and what has happened is this inverting terminal is now grounded. So, what happens to this? This also retains the same feedback, it is still positive feedback, but what happens here is that V naught for large negative voltage here, has to be negative, because this is applied to non-inverting. If large negative voltage is applied, this has to be minus Vs. So, it would start from minus Vs and this will start with minus Vs. The voltage here, therefore, when it becomes equal to 0 here, this is grounded. So, when this becomes close to 0, change of state should occur. What is that voltage which will make this voltage 0 at this point? Vi, this voltage is Vi into R2 divided by R1 plus R2, Vi into R2 by R1 plus R2 plus V naught into R1 by R1 plus R2. If Vi and V naught are the voltages here respectively, Vi into R2 by R1 plus R2 plus V naught into R1 by R1 plus R2 is the voltage here. When this becomes equal to 0, change of state should occur. So, V naught at present is nothing but minus Vs. So, when Vi becomes equal to plus R1 Vs by R2, change of state will occur. So, this will go on like this, and then change of state will occur from minus to plus at a voltage which is R1 by R2 times Vs. So, this is the change of state. It is going to now change state to plus Vs, this from minus Vs. Once this becomes plus Vs here, the next change of state occurs only when Vi decreases, and that will happen when this becomes minus. Same equation is valid. So, So, again you get the same hysteresis, but it is of another type. The output is at minus originally, goes to plus, whereas the output was minus originally, plus originally and goes to minus. So, this is one type of Schmidt trigger or regenerative comparator, that is the other type of Schmidt trigger or regenerative comparator. These two types are commonly used in a variety of applications like signal generation and wave shaping, etc. We will work out an example in order to illustrate one of the applications of positive feedback using this circuit. Okay. So, consider the Schmidt trigger that we had earlier discussed. Let Vi be a sine wave as shown here being applied to the input of the Schmidt trigger. What is the output? We would like to this. So, this could be a sine wave or a triangular wave or an exponentially increasing and exponentially decreasing wave. I am typically discussing this for a sine wave. So, as the input voltage here is increasing, this portion of the circuit, the input voltage is increasing. So, this circuit says the change of state should occur when the input voltage is increasing at beta Vs. So, let us say this is beta Vs, okay, and this is minus beta Vs. Now, change of state should occur. Originally, when the input was negative, output was positive. So, it will start with positive voltage, okay, and at beta Vs it will change state to negative. Let us say it is plus Vs, let us say Vs is greater than Vp. From plus Vs it would go to minus Vs. So, this is the point at which change of state will occur, that is beta Vs. Thereafter, the input voltage is going on increasing, nothing happens until now it further starts decreasing. When it is decreasing, change of state will occur not at this point, but at this point, because at minus beta Vs. So, the next change of state is going to occur at this point, to plus Vs. Again next change of state will occur at this point. So, you will see that for a sine wave input you get a square wave output, but the change of state occurs at levels fixed by the Schmidt trigger, okay, uniquely fixed by the Schmidt trigger, not at any other point. So, this is very useful in converting a periodic waveform like sine wave or triangular wave to a very good square wave, because the rate of increase of output voltage from this to this now totally depends not on input waveform, but only on the maximum rate of rise possible or maximum rate of fall possible for the op amp or amplifier structure that is put here, comparator structure put here. So, this is going to be a very sharp transition here. So, in order to convert a stream of data which has got corrupted because of the line capacitors etc., to exponential increase and exponential decrease, the so called square waves themselves may get distorted to exponential increase and exponential decrease because of line capacitors. Then in order to convert them into sharp transition pulses, this Schmidt trigger is used. This is one application, one important application. Next application, also very simple. Now what we do is, by itself this has two stable states, or this is a bistable circuit. One is plus Vs, another is minus Vs. Now I am going to make it what is called as a stable circuit. Consider this circuit. As far as this itself is concerned, this is a circuit with positive feedback here. So it does not really know what is happening here, let us assume. But the capacitor is initially uncharged. We will consider capacitor is initially uncharged. I switch on the thing. Obviously, we say that this is a regenerative comparator and that output has to be either at plus Vs or at minus Vs, that is for sure. So output is at plus Vs, let us consider. If output is at plus Vs, let us put that down. What is happening here in this circuit, let us independently consider. Capacitor is not charged. So the capacitor will start getting charged through this resistance. So that will be, that you know, is an exponentially increasing waveform. So capacitor will start getting charged this way. What is this? This is going to be charged towards Vs. It will try to go towards plus Vs with the time constant equal to C into R. So the charging time constant is C into R. So it is increasing, this capacitor voltage is increasing with respect to time. So this Schmidt trigger says, if a voltage is increasing at its input, I will change state when the voltage reaches beta times Vs, beta being equal to R1 by R1 plus R2. So since this is plus Vs, this is beta Vs, change of state will occur when this voltage reaches a magnitude of beta Vs. How will the change of state occur? It will change state from plus Vs to minus Vs. Now what will the capacitor see? This has changed over to minus Vs. This becomes minus beta Vs. So the capacitor will now charge towards minus Vs with the same time constant. So the capacitor will keep charging towards minus Vs with the same time constant. But as soon as it reaches minus beta Vs, because the voltage is decreasing now, this voltage is decreasing. So this will say that I am going to change state the moment this voltage reaches minus beta Vs. So again it will go to plus. This story never ends, because now the capacitor is going to charge towards plus Vs with the same time constant Rc. As soon as it reaches beta Vs, this will change state. This is what is called as an stable multivibrator. It keeps changing the state from plus Vs to minus Vs to plus Vs, goes on its own, and therefore it produces a square wave at this point and an exponentially increasing waveform and decreasing waveform at this point, this kind of wave. In fact, you can therefore find out this time interval. This time interval and this time interval will be the same, because the capacitor during this time has discharged with the same time constant as it is getting charged. So, the discharging time constant is same as charging time constant, and the voltages change will be from beta Vs to minus beta Vs. That means 2 beta Vs is what is acquired by the capacitor. So, these two time intervals will be same. That means this is the period of the waveform T. Okay, you can evaluate this by equating, let us say that this is exponentially changing e to power minus t by RC, right, 1 minus e to power minus t over RC. This is the way voltage changes. Okay. The voltage applied here is from minus beta Vs, it is trying to go towards plus beta Vs. So, the total voltage applied is beta plus 1 Vs from here to this point, okay, assuming that this is 0. So, from here to the top point it is beta plus 1 Vs, and it is going to change at 1 minus e to power minus t over RC, that kind of rate. But voltage acquired within t by 2 is twice beta Vs. That means, during this time period t by 2, the voltage acquired is twice beta Vs. From this equation, t comes out as, okay, if you write down Vs gets cancelled, okay, you have you can equate this, t comes out as RC log 1 plus beta by 1 minus beta. That is this is t by 2. T by 2 comes out as RC log 1 plus beta by 1 minus beta, or t is equal to twice RC log 1 plus beta. So, you can therefore evaluate the frequency of oscillation of this a stable multivibrator if you know the resistance, capacitance and the beta value. This circuit is useful as a signal generator. It is commonly used in signal generators, and you can see that the basic principle is very simple. It is using some kind of integrator here. This is a rough integrator. Capacitor getting charged through a resistor is equivalent to an integrator, and this is the Schmitt trigger. This integrator Schmitt trigger combination is a common circuit for what is called as function generation, right, or waveform generation. We had digressed a little bit. We were discussing negative feedback configuration. In order to differentiate it from positive feedback, we went over to positive feedback configuration. For example, this is a negative feedback configuration. To show that structure looks similar with this minus, this plus, but that structure is entirely different. That is one with positive feedback, regenerative positive feedback, and with hysteresis, when this becomes plus and that becomes minus. Similarly, when this becomes plus and that becomes minus, that is another regenerative feedback configuration. So, this should be kept in mind, that the feedback changes, the characteristic becomes different. That is a nonlinear circuit. This is a linear circuit with a gain of 1 plus R2 over R1. So, continuing with the basic negative feedback configurations, this is a buffer unity gain amplifier. This is a non-inverting amplifier of gain 1 plus R2 over R1, which we had discussed, and this is another important configuration called inverting amplifier. So, just compare this with the two configurations for positive feedback that we had just now discussed. These are regenerative positive feedback with different characteristics. Okay. So, one was non-inverting Schmitt trigger, another was inverting Schmitt trigger. Now, coming back to the negative feedback, let us see how we can generalize this negative feedback configuration here. This is an inverting amplifier with R2 over R1. When I ground this, what we said was always this is at virtual ground, as long as output is connected to input. Please remember that For this to be at a virtual ground, the condition is output should be somehow connected to the input, somehow. It does not really necessarily get connected like this. It can be connected in any manner that there is negative feedback. Then this can be at virtual ground. Such a situation, this becomes a current summing node, because at this point the potential is always 0 and currents can get summed up. So, this property can be used in summing current. So, this is actually I1 IN. So, the entire current is going to flow through this RF, appear as this current is going to be sigma I equal to 1 to N. That, therefore, the voltage here is going to be that summed up current gets converted into a voltage which is minus, because this is plus and that is minus, sigma I is equal to 1 to, or we will call it Ij in order to differentiate it. J is equal to 1 to N. So, this is into R, that is the scaling factor RF. So, this is therefore going to be called as generalized, as a summing amplifier. Sigma I J into RF, J equal to 1 to N. So, if I want, for example, resistors connected here, R1, V1, R2, V2, so on, Rn, Vn, then all these currents Ij's can be replaced by Vj's by Rj's, because Vj is equal to Ij is equal to Vj by Rj, because this potential is 0. So, you can therefore get this output as minus Rf, let us say we will call this as alpha 1 times R1, alpha 2 times R, this is alpha n times R scaling factor, then this will be sigma, this alpha R will come, Vj divided by alpha j, right, j is equal to 1 to. So, if you have Rf by R equal to 1, then the coefficients of Vj's can be conveniently chosen as 1 over alpha j's. So, this becomes a very convenient summing amplifier. Now, I am going to further generalize. I do not have any choice regarding the sign of the coefficient here, but the value of the coefficient can be greater than 1, less than 1, anything. So, it is a very simple design. Now, let us see whether we can have a means of controlling the sign as well as the magnitude, so that it becomes a generalized summing amplifier. Consider this circuit simply. At all times we only give negative feedback, that you should remember. This is VA, this is VB. what is the output V naught if let us say this is R1, this is R2, this is R3 and this is R4. That is a general configuration. Let us see how to evaluate this. We can do this by superposition theorem because there are two voltages. Okay. We can do this by superposition theorem. First find out only for one voltage, other voltage being connected to ground, okay, and then find out for the other voltage. Now, considering that VB is connected to ground, let us find out the output for VA. Now, this becomes nothing but the inverting amplifier shown here with R2 and R1. If you are grounding this, this potential is 0. So, it is almost equivalent to this circuit. So, this becomes an inverting amplifier. So, V naught is nothing but minus R2 over R1 times VA. With VB connected to ground, it is equivalent to just an inverting amplifier there. Next, let us lift this above ground. This is VB. Connect this to ground. Now, what does it become? From here to here, it is an attenuation. So, the voltage here is VB into R4 by R4 plus R3 attenuator, and from here onwards it is nothing but the non-inverting amplifier there. So, it is the same configuration. So, gain is 1 plus R2 over R1. So, this is plus VB into R4 by R4 plus R3 into 1 plus R2 over R1. So, this is the composite output of this amplifier. This is therefore equal to, this has a negative sign, you see, this has a positive coefficient, right. So, let us say I would like to make this a difference amplifier. There are two voltages. I want to take a difference of VB and VA. Therefore, I would like to take this as common factor. Let us say R2 over R1 minus VA plus, okay. This should have been plus VB, minus VA plus VB would have been the differential thing. So, I have taken out R2 over R1. So, this becomes 1 plus R1 over R2 divided by 1 plus R3 over R4. I am dividing by R4. So, 1 plus R3 over R4. This R2 over R1 I have taken out. So, this becomes 1 plus R1 over R2. So, that means if, this is important, if 1 plus R1 over R2 equals 1 plus R3 over R4, that coefficient becomes 1. So, this becomes R2 over R1 into VB minus VA, a difference amplifier. This is called a difference amplifier. What is the condition? This one gets cancelled. So, R1 by R2 should be equal to R3 by R4. If you make R1 by R2 equal to R3 by R4 equals 1, then this gain also becomes equal to 1. It is ordinary difference amplifier. Output is VB minus VA. Such an amplifier is necessary in all bridge measurements. You want, for example, the bridge voltage comes as a difference voltage VA minus VB or VB minus VA, and I want to amplify this by a factor R2 over R1. So, this is a common amplifier configuration which is used along with bridge, right. So, where do you use a bridge? Maybe in resistance measurement, okay, capacitance measurement. In all these measurements you use bridges. And where do these bridges become necessary? whenever we have transducers whose resistance varies or capacitance varies or inductance varies and we want this variation to be measured, we form them into bridges, so that the common voltage gets cancelled and only the difference voltage, which is the unbalanced voltage, comes at the input of the amplifier. Okay. So, this forms the basis of an important amplifier called instrumentation amplifier. In almost all the transducers which are coming as bridge, okay, as bridges, this instrumentation amplifier is the first amplifier which amplifies the different signal component. An instrumentation amplifier is therefore basically a difference amplifier. Now, obviously, this instrumentation amplifier might disturb the bridge balance because it is loading the bridge. So, if you want to a good instrumentation amplifier, okay, you have to buffer it from the bridge. Apart from taking a difference, it should also be acting as a buffer, so that it does not load the bridge. Therefore, we will now introduce two buffers here, so that this loading action is prevented. Those buffers are already known to us. They are therefore going to be unity gain amplifiers or non-inverting amplifiers. Any of these could be used as buffer stages. VB, which is not inverted, and VA, which is inverted there. So, we have the buffer stages just introduced here, so that this becomes a good instrumentation amplifier. So, now these three op amp configuration can act as a fairly good instrumentation amplifier with a gain of R2 over R1. But you know, this condition has to be satisfied. R1 by R2 should be equal to R3 by R4. Now, we say that I have the op amp almost near ideal op amp, okay, but the resistors I have chosen are just nominal resistances with some amount of tolerance. So, let us consider that the resistances that we use have a tolerance of delta. The resistance that we have a tolerance of delta. That means R value is going to be R into 1 plus or minus delta. That is what it means. Tolerance of delta means. So, R can be changing from its nominal value by plus minus delta. So, if such resistances are used for fabricating this instrumentation amplifier, this R1 will be okay, R1 whatever value it requires and plus minus delta. So, I want this to merely act as a difference amplifier with unity gain. Let us say R2 by R1 is made equal to unity, this is equal to R4 by R3. So, all resistances are made equal to R and all of them have a tolerance of delta. That means, this is merely being used as a difference amplifier with unity gain. So, what is the difficulty? Now, please recollect what I discussed about in terms of differential amplifiers. Any differential amplifier with a differential mode gain also has a common mode gain, and it has a specific common mode rejection ratio. This I have discussed. What is it? When we want to amplify VB minus VA, or we want to just collect VB minus VA, there will be a common signal between VB and VA, which is VB plus VA by 2. So, it should be capable of rejecting that common signal. What does it mean? When VB equals VA equal to the common mode signal, which is VB plus VA by 2, there should not be any output. because VB has been made equal to VA equal to VC, there should have been 0 output. But because of the problem with this tolerance, what happens, these resistances are not exactly equal. If this is 1 R into 1 plus or minus delta, this also is the trouble arises not if the error is in the same direction in all. If this is R into 1 plus delta, this also is R into 1 plus delta, the ratio is still 1. Here also this is R into 1 plus delta, this also is R plus 1 R into 1 plus delta, the ratio is still equal to 1, and therefore there is no problem. The gain is going to be it is going to have no output as far as common mode signal is concerned. But the problem arises when this is R into 1 plus delta, this is R into 1 minus delta, or when this is R into 1 plus delta, this is R into 1 minus delta. So what happens is that this ratio, if instead of being 1, will be deviating from 1. If this is 1, this also should be 1. Then only this cancellation occurs. Unless this cancellation occurs here and this becomes VB, just VB, this cannot be considered as difference amplifier. So when VB is equal to VA, it is going to still give us an output, okay, if these do not get cancelled. So what is the common mode gain under this situation, worst case common mode gain? So we will want to find out common mode gain, that is AC. CMRR is nothing but AD by AC, the differential mode gain divided by common mode gain. Differential mode gain has been made equal to 1, R2 equal to R1. So R2 equal to R1, okay, AD is equal to 1, okay. But we have to also make R2 equal to R1 equal to R4 by R3, that means R4 also has been made equal to R3 equal to nominally, okay, same value of resistance R. So what is the common mode gain? Then VA equal to VB. This is VC, this is VC now. VA has been made equal to VB equal to VC. So whatever output I get now, what is the output? We will take R2 equal to R1. So this is made equal to 1 nominally. So this is having minus VC, okay, let us say R2 by R1, that is a common factor. R2 by R1 is very nearly equal to 1. This into minus 1 plus R1 by R2 divided by 1 plus R3 by R4. What is this? This is equal to, this R3 by R4 will go up, 1 will get cancelled. So you have minus VC into R2 by R1 into, okay, minus R3 by R4, okay, plus R1 by R2. From this is what you get, divided by 1 plus R3 by R4. So again take this inside, this becomes equal to 1, this is R2 by R1. As before, you see this is 1 minus R3, okay, R4, R3, R2 by R4, R1, R3, R2 by R4, R1. Which should have been equal to 1 nominally. If this is 1, this is 1 minus 1, this is 0. Common mode gain is 0, common mode rejection ratio is infinity. In this particular case, what is the worst case value for this? When all the nominal values are R, this will be R squared, this will be R squared, that gets cancelled, nominal value is 1. Inside the bracket you will have R squared into 1 plus delta into 1 plus delta. So, 1 plus 2 delta plus delta squared. Here you have to consider the worst case situation, 1 minus delta into 1 minus delta. So, r squared into 1 minus 2 delta plus delta squared. If you neglect delta squared, because delta itself is very small, this is the value of the so called 1, or how much is it different? 1 plus delta by 1 minus delta is approximately equal to 1 plus 4 delta. Okay. So, this becomes 1 plus 4 delta. Okay. So, 1 gets cancelled, the whole thing will give you a contribution of only 4 delta, and the denominator R3 is equal to R4, this is going to be 2 nominally. So, this is going to be okay, minus Vc into 2 delta, plus or minus of course. So, the gain AC, right, V naught is equal to plus or minus Vc into 2 delta. So, AC is equal to 2 delta. This is an important piece of information which is needed by any designer of an instrumentation amplifier. If the instrumentation amplifier is designed using resistance of tolerance delta, the common mode gain is 2 delta, right, worst case, that is. The best case value is 0. Okay. So, the worst case value is 2 delta, that means common mode rejection ratio for this simple difference amplifier with gain equal to 1 is 1 by 2 delta. Consider ordinary resistances of 5% or so, right, delta is 5 by 100. So, common mode rejection ratio is going to be 1 by 2 into 5 by 100, okay, that is only 10. Its ability to distinguish between common mode voltage and differential voltage is only a factor of 10, which is a very poor value, and therefore, you have to use precision resistors here in order to get good common mode rejection ratio. So, we are now confronted with a very serious problem in instrumentation amplifier design, that if I have to use actual resistors here, okay, and come out with huge number of instrumentation amplifiers. Now, please be careful. If I adjust these resistances in such a manner that this ratio becomes okay, satisfied, then I can always make AC equal to 0. That means, you can always make an instrumentation amplifier with infinite common mode rejection ratio. But practically what happens is, we cannot keep on adjusting these resistors for each instrumentation amplifier, because for the test alone you will have to spend lot of money. So, the price for the instrumentation amplifier will go up. When a mass manufacture of an unit is being made, you would like to simply connect this and expect it to work satisfactorily. In such a situation, tolerance of resistance becomes important. The resistances used must have good tolerance, so that all of these units that are made will have good CMRR, okay, and the units can be sold straight away without being tested, then they can be sold cheaply. Okay. So, in order to make the instrumentation amplifier be sold at low rates, okay, we must use off the shelf components, okay, without further testing the instrumentation amplifier. In such a situation, we must accept certain tolerance for these resistors. So, how to improve the common mode rejection ratio? This is important. How to use poor tolerance resistors here and still get, okay, better common mode rejection ratio is one thing, and how to buffer, that we have already discussed, is going to be the topic for the next class. Therefore, we will now convert this into, let us say, instead of buffer we will have non-inverting amplifier with the same gain. If you do this, VA is going to be amplified, VB also is going to be amplified by the same factor, hopefully, because same factor is important. Otherwise, again this will contribute, okay, to common mode. So, if these are amplifying by the same factor, VA and VB by the same factor, then overall gain can be attributed by these gain factors. This can be R, 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 R. Okay. But this is not going to solve our CMRR. CMRR remains as bad as ever, right. In fact, it gets worsened because these tolerances also come into picture. I have redrawn this circuit, same circuit, with this resistances put on this side as same as this side, but both of these amplifiers are now giving a gain of 1 plus RB by RA if these resistances are identical, right. Now, there is only one simple trick in order to get over the problem of tolerance, but still give gain. So, this grounding is responsible for the current in this to be made VA by RA, current in this to be made VB by RA, right. The current should be same, VB by, that is determined by the same resistance, okay. But these resistance values, if they differ, the currents will be determined by different value resistance. That can be made same by simply lifting this above ground. Look at this. Both these resistances are lifted above ground and connected together. Now, it simply loses the common mode problem. Only the difference mode voltage will have any say in fixing the current in RAs. Let us see how it is. If this is VA, this is VA. If this is VB, this is VB, that we know, nuller. So, the current in this is now uniquely determined by VA minus VB divided by twice RA. So, the difference is simply taken because of the fact that I have removed the ground connection here. If I had the ground connection, this current would have been VA by RA, this current would have been VB by RA, and those RAs would have been different maybe. Here this resistance determines VA minus VB by twice RA. So, the difference is automatically taken here without the influence of any resistor coming into picture. So, I can make this RA as small as I please and make this difference current as high as I please, and therefore, I can make the differential mode gain alone very high. Have you understood this point? VA minus VB is automatically the difference voltage coming across a common resistance of 2 RA, right. So, VA minus VB by 2 RA can be made as high as you please, but when VA is equal to VB, current is still equal to 0. So, it does not amplify the common mode voltage, it amplifies only the differential mode voltage. This is the trick in the so called 3 op amp instrumentation amplifier. So, if this current is this current will flow through this and develop a voltage here which is VA, this is VA, okay. This will be plus, this will be, so plus VA minus VB by 2 RA into RB, that is the potential here, and this potential here, this current is also going to flow through this like this, develop a drop here. So, VB, which is this, minus, plus minus, so minus VA minus VB divided by twice RA into